Okay, so hello and welcome to today's central exercise session. As usual, we'll take questions on chat. So let me just start screen sharing so that you can see that. Here we go. So our chat channel is available on chat.tum.de. Please use this channel here, MA9714-CE, for questions regarding this central exercise session. We'll spend the first roughly 60 minutes with discussing sheet number 10 and questions related to that sheet. And after that, at 4 o'clock, I'm going to say something about the exam as well. And you'll have questions. You'll have the opportunity to ask questions about the exam then. So please hold back on exam questions until we discuss that topic. Okay, today's chat moderator is Efe. Efe, would you introduce yourself, please?
Hi, I'm Efe from the tutorials, and I'll be taking your questions and forwarding them to Dr. Ritter today.
Okay, thanks a lot. So I guess we start right away. Let's share the screen once again. Okay, you're seeing my iPad screen, hopefully. Problem sheet number 10 is basically about one topic, and that is the integration of a function over a box. So there's only one topic. I guess the poll doesn't make a lot of sense here, so I'm going to skip that for this sheet. We'll have one for the next sheet where there's going to be some more topics. So I'll just start with exercise C10.5. And that's an example of integration of a function over a pretty simple rectangle in this case. So we have a function f, oops, defined on R2 that maps to R, so a real valued function. And that function is given as f of x1, x2 is x1 squared minus 4x1, x2. And the task is to integrate f over the box given by 0, 1 times 0, 1. Or a shorthand for that would be 0, 1 squared. So just to be sure about this, this is the box where both x1 and x2 coordinates vary between 0 and 1. So that means x1 is in this interval here, x2 is in this interval here. Okay, so the box that we have here, if this is 1 and this is 1, then the box we have is exactly this one here. Okay, so this is our domain D, our domain of integration. And we solve the integral. So the task is to compute the integral over f of x1, x2, dx1, x2 over d. So we can easily see that f is a continuous function because it is composed of continuous functions. And d is just a box, including the boundaries. F is continuous over d, so it is integrable over d. And to compute that integral, we can just solve the iterated integral. So we can compute the integral with respect to one of these two variables first, and then integrate with respect to the other variable second. Both are independent. Both coordinates are between 0 and 1 with no dependence here. So whatever order we choose is fine, and the result should always be the same. So what we can do is we can solve the iterated integral in any order as f is continuous on D, and therefore integrable over D. Okay, so this integral that we want to compute, f of x1, x2, dx1, x2 over D. This can be solved, for example, by integrating with respect to x1 first and then with respect to x2. So the outer integral would then be the x2 integral. x2 goes from 0 to 1. And the inner integral, the first one to be applied, will be the x1 integral. And x1 also varies between 0 and 1 here. And the function is x1 squared minus 4x1 x2. Inner integral, that's dx1 first, and then dx2. Okay, so we just treat the x2s as a constant for now and compute the integral of this term here with respect to x1 first. What we get here is first an x1 to the third over 3 minus 4 times x1 squared over 2. So it's 4 over 2 times x1 squared. And we just keep the x2. And again, x1 is from 0 to 1. And we'll still have to integrate the result with respect to x2. Okay, so let's evaluate that inner term first. What we get here is upper bound. Upper bound is 1. So this is 1 over 3 minus, well, 4 over 2, that is just 2, minus 2 times 1 times x2. Minus, and the lower bound is 0, so that is 0 over 3 and 0 times 2 times x2. And we integrate the result with respect to x2. Okay, so what we have here is 1/3 minus 2x2. We're integrating that with respect to x2. And what we get is 1/3 x2 minus 2 over 2 x2 squared. And x2 varies from 0 to 1. So final result, upper bound minus lower bound. So upper bound is 1. We get 1/3 minus 1, and the lower bound is 0. So it's minus 0 plus 0. And that means the final result that we get is minus 2 over 3. So that's the integral of f over the domain D. Okay, that concludes that exercise here. Any questions?
There are no questions so far on the central exercise page.
Okay, great. No questions so far. So just 1 or 2 quick remarks I'd like to make. One is I'm usually denoting the variable of integration with the integral as well. So like this here, I'm usually writing x2 equals 0 to 1, x1 equals 0 to 1. I think that helps knowing which integrals you currently evaluate. So I'd advise you to do that too, but it's not mandatory. The variable of integration is usually denoted by this d. So dx1 tells us this inner integral is over x1, the outer one is over x2. And technically that is enough. So this information is not really necessary, but I still find it helpful. And the same goes for this here, right? Second thing I like to say is in books, in the literature, or in other courses, you'll often find notations using a double or a triple integral or even higher integrals. I did not introduce that notation because it's not very general. The idea of that is to somehow see the dimension of the integral or the domain that you integrate over in the integral sign. Again, this information is not really necessary, and I found it confusing rather than helpful, but you'll often see notation like this. So for example, here, we're integrating this function of two variables over a two-dimensional domain. So that will often be denoted like this, double integral of x1, x2 over dx1, x2. And then the d is just below both of these integrals. Okay, so that's not the iterated integral where you already split up by variables, but it means the same thing as saying we integrate this function over d. You just write two integrals to stress that this is actually two-dimensional. And you would write three integrals if the domain was three-dimensional. So if you integrate over a function with three variables, and then of course, more generally, four integrals for four variables and so on. I choose to just write one integral for any dimension here. Okay, just so that you know what this means if you come across that notation. Okay, have any questions come up?
Still none.
Still none, great. So let's go on to C 10.6 then. So in C 10.6, we have again a function defined on a two-dimensional domain. In this case, it's the interval 0, 1 squared, not including the boundaries this time. So technically, this is not a box, doesn't include the boundaries. And the function is defined as f of x1, x2 equals x1 minus x2 over x1 plus x2 to the third. And you can see that this function is continuous on its domain, but it's not continuous on the boundary. So if both x1 and x2 are 0, then obviously this function is not defined anymore and there is no continuous extension. Okay, so f is continuous on the domain D. D is 0, 1 squared, not including the boundaries, but not on the closure of D, which would be the interval 0, 1 squared, including the boundaries. Okay, and for integration over boxes, of course, what we have to do is usually also integrate with respect to the boundaries. For the integral, if it exists, that doesn't make a difference. Whether you add the boundaries or not, doesn't make a difference for the value, but it might make a difference for the existence of the integral, right? So in this case, we'll see that this integral does not actually exist, even though it is continuous on its domain, because for the integration, we'll also have to care about the boundaries, and it's not continuous there. Okay, so the task of this problem is to show that f is not integrable over its domain. And we can just do that by computing the integral, trying to compute the integral and see what the result is. You will remember, hopefully, that in the lecture videos, we've talked about Beanies Theorem. And basically, that says if we have a function that is continuous over a box, then it can be integrated. And the result can be computed by iterated integration. And the order of integration does not matter. Okay, so if f is continuous over a box, it can be integrated over that box, of course. And second part, if f can be integrated over a box, then the order of integration doesn't matter. So the order of integration does not change the result. And we can apply iterated integration. Okay, so what this means in this case is if the function f can be integrated over d, then we can try iterated integration, and we can use both orders of the variables, and the result should not change. And that's exactly what we're going to do. We're evaluating both possible orders of integration, and we will see that indeed the result does change. And that means the function cannot be integrable. Okay, so we'll apply that here. We will compute the integral of f of x1, x2 over this domain D, dx1, x2 through iterated integration as well. We'll use first the integral where x1 is the outer integral and x2 is the inner integral. So like this. And we'll compare that with the other order where x1 is the inner integral. Oops. And x2 is the outer integral. So dx1, dx2. And if f is integrable, both integrals must actually be equal. And we will see that they are not. So that means f cannot be an integrable function. Okay, so that's the strategy. Only thing left to do is actually evaluate these integrals, and that's what we're going to do now. We'll start with the integral where x1 is the inner integral and x2 is the outer one. It doesn't really matter what we do here. And then we'll try and derive the other one using a shortcut. Okay, so we start with the integral over x2 from 0 to 1, x1 from 0 to 1, over x1 minus x2, and then x1 plus x2 to the power of 3, dx1 dx2. Okay, now how can we integrate that expression with respect to x1 first and then with respect to x2? The trick that we're going to use here is we're going to use integration by parts. You should know that from the first semester, hopefully. If you don't, that's a good time to brush up on that knowledge. We'll frequently need integration by parts, and we'll also frequently need substitution to hopefully revive your memory here. Recall the integration by parts formula. Now, what this is doing is you integrate an expression of the form a function u times a function v prime. And by this integration by parts formula, the result is the same as u times v minus the integral over u prime v. So you integrate one of these two factors, you integrate that v prime factor to get a v, and you differentiate the u to get a u prime. And of course, for that to work, you need to be able to integrate that factor here, so you should choose that carefully. And it should be usable to differentiate that factor u here. So for example, the best case is that factor just vanishes with the differentiation, and then that integral becomes tractable. And actually, that's the case fairly often, or at least it gets easier. Okay, in this case, what we are going to do is we're going to write this expression here in the integral. Let me just write down the integrals first. This expression can be written in the form x1 minus x2 times, and then the denominator, and that is x1 plus x2 to the minus 3. I'll write it like this to make integration a little easier to see. Okay, and what we're going to do now is we're going to use this here as u, and this here as v prime. And if we integrate that part over u here, this one here, no, sorry, if we differentiate that part with respect to x1, then that expression will just vanish, and that will make things a little easier. Okay, so that's the basic idea of evaluating that integral here. So doing that, what do we get? We just keep the outer integral in place. And for the inner integral, we apply integration by parts. And that means, we call that formula here. That means the first part of this expression is uv. So we keep the u, x1 minus x2. We have to integrate that v prime expression. So we have something to the power of minus 3. You get the integral of that by increasing the exponent by 1. So we have something to the power of minus 2, and then dividing by that new exponent. Okay, so this is x1 plus x2 to the power of minus 2, and then we have to divide this by minus 2. And there's no factor in front of the x1, so no complications arise here. Okay, so this needs to be evaluated for x1 from 0 to 1. And then we need to subtract the integral over u prime v. So minus the integral for x1 from 0 to 1 over u prime v, u prime. So if you differentiate this with respect to x1, that's just 1. What's the purpose of this? And we know v already. V is this expression here, minus 1 over 2 times x1 plus x2 to the minus 2. So instead of minus integral, we can just write plus 1 over 2, the integral, minus times minus, let's cancel out, times x1 plus x2 over minus 2 dx1, and the outer integral dx2. Okay, so let's evaluate the inner expression. First, this part here, we have to compute upper bound minus lower bound for the x1, and we just keep the x2 as a constant in here. So what we get here is x1 at the upper bound, that is 1 minus x2 times 1 plus x2 to the minus 1 over minus 1 over 2 times minus 1 over 2 minus, again, this minus 1 over 2 factor, so we get plus 1 over 2, and now we substitute 0 for x1, And then we get minus x2 and plus x2. Okay, so that's this expression. And then we have to integrate this expression. And that works in the same way as I've just shown you. So we have plus 1 over 2 times this integral here. So that will be, you increase the exponent of minus 2 by 1, so you get minus 1. And then you divide by that new integrand. So you divide by minus 1. And 1 over minus 1 is just a minus. So what we get here is minus x1 plus x2 to the power of minus 1. So that's 1 over x1 plus x2, and this minus sign here in front. And this is again for x1 from 0 to 1, dx2. Okay, let's see if you can simplify this expression a little more. So I'll just keep the outer integral in place for now. What we get here is, so here we have a minus 1 over 2. This is 1 plus x2 to the power of minus 2. So 1 over 1 plus x2. So let's just put this in the denominator, 2 and 1 plus x2. Well, sorry. Let's make this a little more readable here. 1 plus x2, like this. And we have this minus 1 minus x2. With this minus here, that becomes x2 minus 1. Okay, so this is this first part of the expression. Then we get minus 1 over 2 x squared, x2 squared. Minus 1 over 2. Did I mess up here somewhere? I did. Right, so that second one, that should actually be to the power of minus 2. Sorry about that. So here I'm missing a minus 2. Okay, so but still that's minus 1 over 2. Let's write it like this: x2 over x2 squared. Okay, and finally, we get minus 1 over 2, and then we evaluate this expression here at the boundaries. So upper bound is again 1. I took out the minus already, so I don't have to worry about that. And then I get 1 over 1 plus x2. And then minus 1 over x2. dx2. Okay, let's see that we can simplify this a little more. Okay, first what we're going to do is, we have here this expression x2 minus 1, and here's an x2 plus 1. I'd actually like to be able to have an x2 plus 1 in the numerator as well, and I just see I have again made a mistake. There should be a square here, right? This one. Or things won't add up at the end. So I'd like to have an x2 plus 1 in the numerator so that I will be able to cancel out one of those, and then hopefully be able to combine it with this term here. It has the same denominator then. So what I'm going to do is I'm going to reformulate that as x2 plus 1 minus 2 instead of x1 minus 1 over 2, 1 plus x2 squared. Okay, then in this expression here, I can just cancel out one of the x2s. So I get minus 1 over 2x2. Here I get minus 1 over 2 1 plus x2. And here I get plus 1 over 2x2 dx2. And now we can hopefully see that this can all be simplified quite a lot. So first, this here, let me mark that in a color actually. So this here and this here, this is the same expression with a different sign, so that cancels out. And here, let me just do this simplification step here. We have x2 plus 1 over 2, x2 plus 1 squared, minus 2 over 2, x2 plus 1 squared, minus 1 over 2, x2 plus 1. And so you can see that this x2 plus 1 expression, that cancels out. And that means I have the same expression, sorry, I have the same expression here, and here. Again, with a different sign, so those cancel out as well. Okay, so what I have left is the integral of x2 from 0 to 1. The 2's also cancel out. And that means I'm left with a minus 1 over x2 plus 1 squared dx2. And finally, that's something that can be integrated pretty easily. We've done that already. So that's of a form x2 plus 1 to the minus 2. So the integration is 1 over x2 plus 1. And the minus sign cancels out with the minus 1 that you get from the integration step. Okay, we have to evaluate that. Again, x2 from 0 to 1. So what we get is for the upper bound 1, we get 1 over 2. For the lower bound 0, we get 1 over 1. So that's minus 1. So the result is minus 1 over 2. Okay, I hope I didn't spread too much confusion with that. Let's see if there are any questions. Efe.
So there was one question asking how did you see that the function is not integrable without testing it? And that was asking the first half.
Actually, I did not see yet if the function is integrable. So I was just telling about the strategy that I was going to use. I have not arrived at that conclusion yet. So I'm currently trying to integrate it first one way, and in the next part I'll try to integrate it the other way. And I just told you what will happen then, which we don't know yet. What will happen then is the two results will be different. And if the function is integrable, then the two results will have to be equal. It will turn out they're not. So that's when we know the function is not integrable. We don't know yet. I hope that helps.
There is one more question that just came now. It is saying, wasn't it just enough to state that the function is not continuous on the boundaries? Can I also state that because the domain of the function is not a box, is it not integrable?
No, you can't just say that. So what we know is that continuous functions over boxes are integrable, but there are other functions and other domains where the integration works out as well. So this cannot be reversed, right? Even non-continuous functions and over non-boxes may be integrable, or they may not be integrable. So this is an example for a non-integrable function for such a case. But there are also examples where this works out fine. Yeah, we'll learn more about that, and we'll also see some examples, I think, in the videos of this week. So we'll see cases where we can actually compute integrals over non-boxes, and even for functions that may not be continuous everywhere. Any other questions?
Yeah, there is one more from Julius. He says, could we also use Riemann sums to show non-integrability?
Could you use Riemann sums? In theory, yes, of course you could. So the definition of integration is via Riemann sums. That means you could also show that lower and upper Riemann sums will not converge or not converge to the same value. I just think this way is far easier here. I haven't tried using Riemann sums actually, but of course you could try that. Anything else?
Okay, and there was one more person typing. It says, could you explain again the last canceling out step, please?
The last
Someone
canceling
says.
out step. So I'm guessing you refer to this one here.
Yeah, I think so.
So let me just a second. So what happens here is that first fraction here. What I'm doing here is I'm canceling this x2 plus 1 expression. So then I get 1 over 2 x2 plus 1. So I'm losing the square in the denominator, right? And that here is precisely the same as this, but with a different sign. So those two cancel. And then, of course, I also cancel this 2 versus this 2. I hope that's the step that you actually meant. Otherwise, just please ask again. Nothing else?
There's one more person typing. Okay, and then that person is asking, could you explain the step before that?
The step before that. So this line here actually has not much to explain, right? Maybe even I'll try. So what happens here is pretty simple. You just take this expression and this expression, and apart from the sign, those are the same, so those just cancel out. That's what's happening here. And the other thing that's happening here is I'm taking this fraction here, and I'm just splitting it up. I'm splitting it up into this first part here, without the minus 2, and that second part here. All right, so this is the first part, this is the second part. And of course, I'm doing this because I want to cancel this factor. Yeah, and maybe go one more step back here. So the way I arrived at this from this here is exactly by this idea of cancellation. So what I want to do is I want to be able to cancel out this square here so that I have an expression that looks like this, in the hope that those will cancel out. And to do that, I need a numerator of x2 plus 1, like here in the denominator, which I don't have. I have x2 minus 1. So what I'm doing here is basically I'm just adding 2, and then I'm subtracting 2. So that doesn't change the value overall. But adding 2 to this expression means I get this x2 plus 1. And then, of course, I have to subtract this 2 again. Yeah, and then after the splitting up, so after I do this step here, I can then finally cancel this expression here to get this orange one. And then it turns out that these are actually the same and cancel out. Okay, so quite a long shot actually, but it works. Any more questions?
It doesn't seem so far. There's one person typing still. Okay, it seems not anymore.
Okay.
Yeah, that's it.
Okay, good. So we still have to evaluate the other integral. So far, remember we evaluated this integral where x2 was the outer integral. Should actually make that more readable, like this. And x1 was the inner integral. So we still have to compare that to the integral where we switch that integration order. Okay, we will now compare that to the integral where we integrate over x1 on the outside and x2 on the inside. So x2 is the inner integral, x1 is the outer integral. And we will see, as I told you already, that these will not match up. Okay, so how do we do that? Let's evaluate that integral. So x1 from 0 to 1, x2 from 0 to 1. And the function is again x1 minus x2 over x1 plus x2 to the power of 3 dx2 dx1. Okay, so what we could do now is apply pretty much the same techniques that we just applied for this first integral, and we would hopefully arrive at the correct result. I'd like to propose a shortcut here that simply works by mainly going back to what we already computed with the first integral. So the idea is to first flip the role of the two variables in the inside, in the integrand. So we just keep those integrals here as they are. And then we flip that. So I want something like x2 minus x1 over x2 plus x1 to the power of 3. I can, of course, do that here in the denominator. There's a plus sign, so I can flip it any way I want. There's a minus sign here, so I cannot just flip that, but I can take out a factor of -1. So this way would be correct, right? So I write this -1 here in front of the integrand. Right, that doesn't change the integral. And now I have something where, at least in the integrand, the roles of x1 and x2 are reversed. So let's take this minus out of the integral, so I can do that. Integration is linear, so I can just take out the minus sign. And then what I'd like to do is, I'd like to say, well, this is pretty much the same integral that I have just computed. So couldn't I just use the result from above? And I can, technically, if I do a small substitution. So what I do here is I substitute a variable I call C1 for x2 and a variable I call C2 for x1. Right? If I do that, the differentials of those will simply be 1. So no extra factor happens. And that means what I get is, well, I can just replace x1 by c2. And of course, that also will go from 0 to 1. And I replace x2 by c1. So this, again, will go from 0 to 1. And then I also replace those in the function expression itself. So I have c1 here minus c2 divided by c1 plus c2 to the power of 3 dc1 dc2, like this. What I have now is the very same integral that I have just evaluated. The only difference is I now have c's instead of x's, but the order is the same. So that means I know the result of this integral. It doesn't really matter whether I call the variables x or c, right? It's only the order that matters, and that's the same that I already had. So this is minus, and then I'm just taking the result that I had computed here, and that's -1/2. So the result of this integral is +1/2. And that means what we get here is a different value. So the order of the integration changes the value. And that means for Beanies theorem cannot apply. And that, of course, means the function can actually not be integrated over this box here. Okay, so value changes for different order of integration. And what that means is f is not integrable over this domain D. And that was what we had to prove here in this problem. Okay, so that's problem 10.6. What questions are there?
Someone asked, is there an easy way to find the critical domains where a function might not be integrable?
The critical domain. So generally, of course, if the function is continuous on a domain that is closed, so including the boundary, then everything will be fine. But otherwise, there's no easy way to find what may go wrong, what may not go wrong. Unfortunately, no.
There's one more question asking, what can be a good sign to a function not being integrable, even if it's continuous?
A good sign to a function being not integrable. So if the function is continuous and you have a closed domain, then everything is good. Then the function will be integral. You don't have to worry about those cases. So basically, you only have to worry about non-continuous cases. Problem is we only have defined integration first over boxes where the boundaries were always included in the box. So we always had a closed set which to integrate over. To extend that definition to arbitrary sets, I hope you've watched that one video already where I explain that. What we do is basically if we want to integrate over some set D that is not a box, then we can define a function f on some box that contains D. And that function is simply defined as, well, I call that fb here, contrast to the original function. So basically I'm extending the original function f from D to some enclosing box by saying I just take the function value f of x if x is actually in D. So where the function is defined, I just take that value. And everywhere else, I just put a 0. So if x is somewhere in the enclosing box, but not in the original domain, I just make that function 0. And then I define the integral over D, f of x dx, as the integral over that box B of fb of x dx. And of course, the problem with this definition is that fb will usually not be continuous, right? So at the border, at the boundary of that D, it jumps straight to 0. And if D does not happen to be 0 anywhere at this point, or it has a limit of 0 at least, then of course this will introduce incontinuities. And that means we usually, if we have arbitrary sets, we usually deal with incontinuities. And that makes things somewhat unpredictable. So it's not easy to say if a function can be integrated over such a set or not. Generally, there's a large class of sets where everything is fine. And again, this week we're discussing one possible class of those sets. But there's always sets that are on functions that are a little strange, where not everything might be fine. And there's no good way of telling that beforehand. So generally, if you have something that is either not closed for the domain or not continuous, then you might be in trouble. And then if you're doing something like this iterated integration, at least take the time to check whether the order may influence the result or not. Okay, I hope that answered the question somewhat.
There is another question asking that they did not get the last steps with the Z substitution and asked for that to be if possible, repeat it. Yeah.
Okay. So actually what I'm doing here, so this is the integral with just x's. And now I'm doing this substitution, right? First thing, I'll substitute C1 for x2. So maybe I'll just copy that part here and do that one first step. The other step is just the same. Okay, so that was the integral here. And now I say my first substitution is I'm introducing a new variable I call set1, and I'm setting that equal to x2. So I'm going to substitute x2 for set1. Then what I have to do, rule of substitution, I have to compute the derivative d set1 by dx2. That is obviously 1, right? So that is x2. So x2 differentiated with respect to x2, that's 1. So that means dx2 is the same as d set1. Okay? So what I do in this first substitution step is I'm not touching the x1 here. This x2 integral, that will now be changed. Usually when I do substitution, I have to change the boundaries according to the substitution. In this case, I just use my old boundaries, put them here into that equation and compute the new set1 boundaries from that. So the boundaries for set1 are, well, x2 evaluated at 0 and at 1. And of course, well, that is just 0 and 1 again. So the boundaries don't change. And then I change those variables here. So I have an x2 here, and I have an x2 here. I change those. So I get a C1 here, and I get a C1 here. And I'm not changing any of the rest. And then, as I said here, the dx2, that needs to be substituted by dz1. So instead of dx2, I'm writing dc1. And again, I keep the x1 part. Okay, so that's the first substitution step, where I substitute C1 for x2. And then I'm doing the same thing with this other substitution here, where I substitute x1 by C2. Yeah? Works just the same. And after you do that, you have basically the same integral again as you had before in that first iterated integral computation. I hope that answers the question. Does it? Or are there
They did
any
not
other
reply,
questions?
but I think so.
Okay.
And there's another question. Yeah.
No other question?
Oh wait, there is now one that says, how did you come with the negative a step for, or the negative step for?
The negative step what?
Well, there is a negative sign, but
I
I'm
guess
not
you
sure.
mean this one here?
Yeah, I just explained that in the chat to somebody else, I think, but.
So let me go back here just a second. So we started with this expression here. And what I did is I reformulated that by exchanging the order here. So I can freely exchange the order in this plus part here. If I want to exchange the order of x1 and x2 here, then I have to factor out a minus. So that's the same as this expression here. That's where this minus comes from. And then I'm just taking that minus out of the integral. Right? And that's what I have here in front of the integral. That's where this is coming from. Okay. Any more questions?
No, that's it.
Okay, so I'd say let's take a very brief 4-minute break, because I promised I'll start talking about the exam at 4 in case someone still wants to join. And then I'll give you a few more details on the exam. I've prepared a short presentation about that. And after that, I'll be taking questions.